In this clip, we're going to learn about a very important inequality in mathematics called the Cauchy Schwartz inequality. These are two different mathematicians. I'm sorry, I don't know much about the history, but this is the name of the inequality. And as usual, we are in an inner product space, always over the reals in this course, though there are inner product spaces over the complex numbers. So we'll assume that u and v are two vectors in an inner product space. It's always true that this inequality holds. Now let's look at it closely. This is the inner product of u with v. The inner product of two vectors gives us a scalar, a number. And as a number, we can take its absolute value. So it'll be a non-negative number here. On the right-hand side, the norm of a vector is also a scalar, a number. Happens to be also non-negative. But at any event, we have a number times a number. So this is just an inequality that one number is less than or equal to the product of these two numbers. And I think we're going to prove it. I mean to say, let's prove it. So here goes. Now, we'll start off with assuming that u here is not equal to 0, because if u equals 0, then the left-hand side is 0, because 0 inner product with anything is 0. And the norm of the 0 vector is 0. So we'll just get 0 less than or equal to 0, which is true. So that this case is dealt with separately. So for the rest of the proof, we're assuming that u is not the 0 vector. Now let's say that x is a scalar, that is a real number, like we said. Then I claim that this thing squared is bigger or equal to 0, basically because anything squared is bigger or equal to 0. So this is a number, the norm, and squared is bigger or equal to 0. Now remember that the norm of anything squared is the inner product of it with itself. In case you forgot, I'll remind you, because the norm of any vector, say v, not necessarily that v, is defined to be the square root of the inner product of v with itself. If we just raise both sides to the power of 2, I could put a 2 here and get rid of the square root, and then we'd get this equality for any vector v. Okay, so back here, the norm squared is the inner product of it with itself, and because of it's bigger or equal to 0, this is bigger or equal to 0. So far, so good. At this point, we expand this using linearity, homogeneity. We've done this kind of thing before, so I won't dwell on the details. Basically, we have xu with xu, xu with v, v with xu, v with v, four inner products. We add them. We also take the constants, the scalars, outside. So this gives us this expression. And the middle two are the same because of the symmetry property. So these two combine to give twice uv with x. Also, remember that the inner product of something with itself is the norm squared. So I did that and put it in front of the x squared. And here also the inner product of v with v is the norm of v squared. So this is the place where we're at. And what I have on the left is a quadratic expression or quadratic function of x. And we can call this part a, this part b, and this part c. Then we have ax squared plus bx plus c. And it's bigger or equal to 0 for all x. Now I hope you remember about quadratic functions. What I want to do is draw a rough sketch of this quadratic function, which is that y equals ax squared plus bx plus c, the left-hand side. Now notice that a is bigger than 0 because, well, it's something squared, and also u is not 0, so a is not 0, so it has to be positive, which means that this is an upward facing parabola.